Hello everyone, my name is Randolph Yao, a data scientist at Microsoft Azure. Today, I will be presenting our work on infusing ML into VM provision in cloud on behalf of all authors of this paper. This talk will be focusing on how we address system challenges integrating ML solution and then come up with a data-driven system design. We also share at the end 2 papers published about the algorithms being used in the solution. Cloud computing has become a powerful computing paradigm. Provision computation resources, like virtual machines, fast and reliably is a critical yet challenging problem. Provision VM is a fairly complex process. The customer begins to specify the VM configuration. The cloud provider will retrieve the matching image from its image repository, copy the image to the customer's account, select the physical node to allocate a customer VM, create a VM with that image, and boot it up. Once the VM is started, it needs to go through a setup process, which provisions the VM from a generalized image to a specialized image with customer settings. Also, all the network connections need to be established to communicate between customers' VMs. Despite the speed increase in modern CPUs, many factors could affect the VM provision time, such as operating system, network speed, resource of the physical hardware, the load on the virtualization stack, etc. Traditionally, when customer requests for a new virtual machine, the virtual machine was created from scratch. It could take a few minutes for the customer to wait before the VM is ready for consumption. With small chance, the VM creation process could also fail due to various reasons. It degrades the customer experience and makes it challenging to meet the cloud auto-scale slogan, or to adapt rapidly to the ever-changing demand. In order to drastically reduce VM deployment time and improve reliability, we are tasked with infusing ML into the provision system. The idea is to break the long sequential steps involved to provision VM into 2 phases. The offline phase to create a partially provisioned VM without user-specific settings. And the online phase involves to convert a partially provisioned VM to a fully configured VM with user-specific settings without reboot at the customer request time. Similar ideas are used at Subway, where food are semi-prepared offline. Upon customers' request online with specific requirement, Subway just need to compose and convert partially prepared ingredient into user-specific requirements. It is very natural to use machine learning to predict VM demands and prepare them in advance. This motivates infusing ML into the overall provision system to make it more intelligent and for better customer experience. At a high level, the prediction service needs to be low latency, adaptive, reliable, and scalable. To make prediction actionable, one important aspect is to predict with sufficient lead time so that the correct type of VMs could be prepared in advance to the customer requests. Telemetry data from cloud infrastructure has tremendous volume, and to identify various properties associated with VM deployments, we also need to join multiple data sources. Hadoop-style batch processing will not satisfy the latency requirement. Azure Data Explorer is a powerful platform capable of online analytical processing, known as OLAP, workload on very large volume of telemetry data. We do incremental processing and cache the processed data back to Azure Data Explorer for future lookup. When the prediction needs to load historical data, it performs join and aggregation for the latest data on the fly, and then union with the cache data to form the entire history, all done in Azure Data Explorer. Many applications move to cloud for fast adaptation to workload changes. The prediction service needs to quickly adapt to those changes as well, which implies the historical data or even trained models could quickly become outdated. Retraining one highly complex model could be very expensive and took a long time to complete. A prediction model with high accuracy wouldn't benefit customer unless the prediction result is generated within limited time budget window. Instead, we trade off prediction accuracy with low latency predictions. We train different models for different type of VM configurations with incremental complexity. We group VM models according to their trained latency and run more complex models only if needed. The best model out of all executed models will be picked for serving. Thus, we are able to retrain models frequently to keep up with the changing demand patterns. How to consume the prediction results reliably is also very important, but often neglected topic. If VM provision service simply try to create as many VMs as prediction recommended, it will be very fragile upon operation timeout, creation failures, or VM become unhealthy after creation, etc. We use goal state-driven system design to improve reliability. By setting the prediction as a goal state of the VM pool size, the number of VMs to be created depends on the diff between the goal state and the current state. Also, once the VM becomes unhealthy or customer consumes VM from the pool, a new VM creation process will immediately kick off to backfill the pool to reach the goal state again. To be able to serve prediction results reliably at a global scale, the prediction needs to have a reliable model serving platform that has high availability. We leverage Resource Central, a general ML serving system that has been deployed to Azure clusters worldwide. The serving is partitioned into regional levels and was able to serve clients with low latency prediction results. Overall, here the boxes in gray are the ML integration components. Just to recap, we use Azure Data Explorer as a low latency data source with incremental data processing power, use Databricks as the main offline training environment to run models of incremental complexity. And we use goal state-driven approach to integrate into ML provision system and leverage Resource Central to scale reliably at a global scale. The system has been deployed and running in Azure for a few years and demonstrated significant improvement in deployment latency and reliability. Thank you everyone for attending the session. Here we attach the 2 published papers on the machine learning aspect. If you are interested, please check it out. For any other questions, feel free to send us emails. Thank you.